Actually, the talk was a joint work with Professor Hayashi. This is physical layer security we have heard a few times in the morning. And I would like to actually narrow down to this two-way Wiretap channel. And this is not, please don't expect me to have some applications of the physical layer security because I'm from the industry, but this talk is really pure theoretical and fundamental limits of this two-way Wiretap channel. Okay, so the content of my talk, first I will explain the problem setting, and then I will focus on this non-adaptive coding over the discrete memoryless two-way Wiretap channel. I will basically focus on the reliability analysis and the secrets analysis. These are the very fundamental results because we derive this error and secrecy rates exponents. So we can use also for the analysis for other channels and problem settings. And of course, based on the code, this non-adaptive coding, and we could derive some achievable rate regions. And also after that, I will give a short summary or overview of the more results we have derived on this topic, and I will conclude at the end. I think the audience, at least I know some of you quite familiar with this channel model. I didn't mention too much about the literature or the history of this two-way channel. I actually try not to touch this channel as this is a well-known, quite difficult topic. I think it's well known that even the communication limits, the fundamental limits, the capacity region is not well established yet. So which means the derived inner bound and the outer bound doesn't coincide. And there is actually counterexample in binary multiplying channel that there are achievable rate pairs which beyond the inner bound, but then, yeah. So this is a very difficult topic in general to deal with. And now we even consider not only the reliable communication, but also the secure communication. So of course, the goal is to design the encoder and decoder, and so design the code to achieve both the reliability and security. And as the title has, as the title indicates that we focus on the non-adaptive encoder. I think you also, this is basically also used by the classical Wiretap channel. So we could see that the encoder just encodes M1, just based on the M1. So to have the code word, to derive the code word of X1N. But the adaptive encoder, we actually see that it's more powerful because it considers the previous feedback, or because the user one basically, it not only sends the input X1, but also receives the output Y1. So if you consider in T time slot, so at time T, he actually could take the feedback from the channel, what he has received so far, like Y1 until T-1 into consideration to encode X1T. So this is basically the big difference of the adaptive encoder and the non-adaptive encoder. Of course, adaptive encoder is more powerful, and when we consider the converse proof, basically we have to consider the adaptive encoder. But non-adaptive encoder makes most of the time the proof or the analysis much simpler. And also the cost function. So basically the cost function is a cost constraint was imposed on the code words. And there's two kind of, we put it here, we classify here. So one is the peak cost constraint. So peak cost constraint means that this constraint is actually imposed on every code word. But the average cost constraint is basically a constraint on the average of the code words. And from the decoder part, we also see that from the literature, there are different decoders. And the first one, or from the classical Wiretap channel, they consider the decoder one, actually at the user one, he has already his own input. He could consider it as a set information. And especially when the encoder is using a deterministic channel, deterministic encoder, then X1N could be derived from X1, and these are available for the at the decoder one. And decoder of type 2, and basically when we consider the secure communication and at the encoder, we often use the stochastic encoder. So here we in this topic, or we mainly consider the decoder of type 2. So which just means that at the decoder one, only we consider X1N as a set information to have to decoder of this Y1. Okay, so from the performance part, as mentioned at the beginning, we would like to achieve the reliable and secure communication, but we know that there are different reliability measures and also security measures. So reliability measures, there are average probability of the error decoding could be used, or the maximum probability of error decoding. So I think people working on information theory, these fundamental limits are quite familiar with these terms. And also for the security, and there are different distance measures could be used for the to measure the information leakage, or basically the distance between two different probability distributions. And also the secrecy, because we are considering two users, and this also could be applied to the multi-terminal cases. And the secrecy could be on different messaging sites, of course. So we could consider the eavesdropper could have just the interest on certain sites of the messages, or there's a stronger one, we consider the whole set of the messages, we call it joint secrecy. And also there are different secrecy strengths, because there are many, at the beginning, it was many research on the weak secrecy. And this basically consider, for example, if we take the error divergency as a measure, as a difference measure, then this weak secrecy basically is a normalized term, so information leakage per channel use. And the strong secrecy basically is the absolute information leakage in N channel uses. Of course, once we have the encoder and decoder, and we could derive the achievability region. And especially when we assume the message side are independent, and we have this read region of the form of the entropy M1, M2. So we could get a summary of the problem setting. So the thing we do this is we know like a problem well defined is a problem half solved. So once we here I just list we have what we have mentioned about the encoder, what kind of coding is used, and what kind of constraint, or if there's constraint at all, or decoder, and also the performance evaluation on the reliability and the secrecy. There are many literature, so people may choose different settings, and this list also help us to compare the results from different references. And in this talk, I mainly will focus on the non-adaptive encoder, and of course as I has mentioned, the second type decoder is considered. And for the reliability, we consider the average probability of the error decoding. And for the secrecy, I will mainly consider the joint secrecy and of course the strong secrecy. Okay. Non-adaptive coding. So as I had mentioned, so this means like each code word is ID generated and also independently selected. And here we have mentioned for secrecy problem, we often choose the stochastic encoders. So it means for each message, we also kind of add some randomness. And in Gaussian kind of channel, they call this kind of like cooperative jamming. This could help to confuse the eavesdropper. And for the reliability, so we use the average decoding error. And for the secrecy, we take the information leakage and we try to derive the strong secrecy rich region of this encoder and decoder pair. If we have a close look to the reliability, actually, we try to correct the error exponent in the sense that we not only see that simply, okay, the error probability of decoding could be made arbitrarily small, but also we characterize it as kind of exponential function, e to the minus an if string, and we give kind of like a function of this if string. We try to characterize this if string. And since we have two users, we, of course, the decoding error could be bound by the union of this decoding error by each user, the summation of it. And we just need to consider one, the error decoding error probability at one user, and by symmetry, we can derive also the other, could apply to the other. For the error exponent, I think many of you are familiar with Gallinger's bound. It's also called error exponent function. So here, basically, I don't want to overload you with mathematics, but here a little bit of mathematics is necessary. So here we see that if we actually could make the formula more this error exponent function in a more cleaner form if we apply the definition of Simpson's definition of the Rényi mutual information. But we know that the Gallinger's bound is for one transmitter, one receiver case. And here we can generalize this Gallinger's bound to our situation with the consideration like input is x1, but we have at the output x to n and y to n, I think. Sorry. Oh, it's not. Yeah. Okay. So this is basically our consideration. So we can consider the input x1n and with the output x2n and y2n. So we can apply Gallinger's bound to our setting, and basically we have a form like we can easily just replace y by x2, y2, and x by x1, and also the property that x1, x2 are independent because we are applying here non-adaptive coding. And then we have a form like this error exponent in the form of conditional range mutual information. But here I have to remind you that this range mutual information is actually the definition as Simpson's definition and also Caesar's definition used, as we has defined in the previous slide. Okay, somehow Yeah, so this definition, because later when we come to the secrecy analysis, we also have a range mutual information definition, but it's different from here. I think the term is minimum over QY. So this is a difference. Okay. And this conditional range mutual information, we see that they also have a very useful property, which means when rho is approaching 0 and it's actually converges to this conditional mutual information we are familiar with. And from this term, we see clearly that the error probability of decoding is exponentially decreasing if we if the rate is under this conditional range mutual information. Yeah. So this is for the for one receiver, and this when we apply to both sets, we actually have a constraint. We derive the rate constraint on both encoders. So to have the reliability, to achieve the reliability, and we can characterize this error exponent in terms of this conditional range information and also the rate you impose. So this is a graphic illustration. We have the code word, and basically this R1, R2. So basically these are the rate constraints for the reliability. And under this rate constraint, our analysis shows this exponential decreasing error probability of decoding. Now let's come to the secret part. Basically, it's similar. And when we consider the secrecy and we do the secrecy analysis, and basically we focus on the information leakage at the eavesdropper, and we see that from the eavesdropper's perspective, it's basically a MAC channel. And we and to bound this mutual information, we actually consider the expectation. We know that the fundamental limits, we always, it's basically a existence proof. So we try to bound this mutual information actually by the summation of this information divergence, but given the two different distributions of Zn, so one is given for fixed M1, M2. So basically you see that if the M1, M2 is fixed, the Z is quite dependent on the randomness you add to. Yeah. And here, I suppose that we are familiar with the relative entropy definition, and also the mutual information can be expressed in terms of this relative entropy. And a further step is that to for this case, actually, as we have mentioned from the eavesdropper's perspective, basically this MAC channel. We already have some results on the key transmake MAC, and we have this resolvability lemma. And basically the divergency can be, the idea to bound the divergency is to use this range relative entropy. And of course, this similarly as an extension of the mutual information we have here, also range mutual information, we see that the definition is a little bit different from the one before we used for the reliability analysis. That's why we use the arrow to denote the difference, to highlight the difference. We basically apply this, we could apply this lemma to the two transmit MAC case. So this is what we could directly use. And then recall that we want to bound the two different, the divergence of these two different distribution, one for fixed M1, M2. Then once M1, M2 is fixed, so the rate for the randomness actually is important parameter here. This is R1R and R2R, and also the summation of it. So this step is basically we apply the reliability lemma. For our scenario, we can see we derive the rate constraint on the randomness that need to be imposed or added in the encode at the both encoders, so that to guarantee that the absolute this information leakage is exponentially decreasing. And we similarly, I also could characterize this secrecy exponent as this rate for the randomness and the mutual information, mutual information. Yeah. So this is here we give again a graphic illustration of this rate constraint to achieve the secrecy. And if we put all the rate constraints together, we show that the secrecy rate basically is the rate pair R1S and R2S, and we apply this Fourier-Moleskine elimination, and we can derive the rate region. And of course, it's worth mentioning the rate region is not new, so it was already in previous work I mentioned here, Perrot and Bloch, they have derived the same region for the strong secrecy. Also for strong secrecy, but the difference is that we actually characterize this error and secrecy exponent. And for adaptive coding, so as I said, this so far we just focus on the non-adaptive coding, but basically we could build also adaptive coding schemes based on this non-adaptive coding, and we could get extended achievable region. I won't go into these details, and I put the reference paper here. But basically, again, so this rich region result is not new for weak secrecy and for strong secrecy. Here, I only mentioned the strong secrecy result, the reference here from Perrot and Bloch. And basically, the same region is derived. And again, our addition, our contribution is mainly the error and secrecy exponents. As I had mentioned, so these are very fundamental block of fundamental analysis, and this can be easily applied to other problem settings. So we just focus on the joint secrecy setting, and we can use the same analysis to the individual strong secrecy analysis, and we can derive the rich region for non-adaptive coding and adaptive coding. So. And also with a few words with cost constraint. I won't go to the details. Yeah, for the cost constraint, we see that this constraint, we consider only the peak cost constraint, and this is really imposed to each code word. And the idea is to use a constant composition code, and the code word has a very same type. So it means all the code words from the same time, they will fulfill this peak constraint, cost constraint. And also we use the method of the types. And here to characterize this error and secrecy exponent, we actually need another version of this really mutual information. You already see 3 different versions in this research of this really mutual information, but these are really very, this help us to get a clean and neat form in the analysis. Okay, here is the conclusion. Basically, we also identify some special cases where non-adaptive coding is sufficient, and but we see that the observation is that the adaptive coding can kind of generalize or enlarge the rate region meaning on the individual rates, but for some rates somehow we didn't have the adaptive coding to actually enlarge the sum rates. That's actually one of the main open problem is there new adaptive coding that could actually improve the sum rate. And also the converse proof which is always very difficult to achieve, or maybe we can, as we have done so far, focus on the special cases where adaptation is useless. Yeah, I think that's all. The rest is just the references.
Thank you very much for your talk.